Okay, good afternoon, lads and ladies. Give me just one moment to get the document camera up and rolling, and we are going to get started. Lately, we've been talking about a lot of stuff. We've bounced around quite a bit. Derivatives, antiderivatives, then areas, and now integrals. And I want to make sure that you guys all have the notation clear in your heads. What means what as far as the symbols are concerned. Ooh, it looks like I might have left my pen downstairs. Okay, I'll be right back. Maybe I need to grab one of the pens. All right, sorry about that, guys. Like I was saying, I want to make sure you're getting all the notation clear in your head and the concepts are not confused. Before we move on to our next topic, now, if I recall, the last thing that we talked about, I'll switch on my screen share here. All right, here we are. I've been subbing for another Calc 1 class lately because we had an injury in the department. Where are we? So we've talked about the fundamental theorems of calculus, yes? Fundamental theorem 1 and 2. Have we talked about indefinite integrals? I don't think we have. So I think maybe today we're going to move into 5.4 and talk about indefinite integrals and the net change theorem. And then we'll also be talking about applications a little bit, right? So that will be fun. And then we're going to talk a bit about differentials, the mean value theorem for integrals. And then we're going to move to U substitution. So today we're going to be finishing up this stuff. So let's get to it. It's working? It is. Okay. So we're going to talk about indefinite integrals and net change. The indefinite integral is not a frightening new thing that you have to learn a lot for. It's really just a bit of notation. So if I give you little f of x and ask for the most general antiderivative first, you find kind of a core antiderivative, right? Like you apply your power rule or your rule for exponentials or whatever you remember for trig functions. You find a function that is an antiderivative. Satisfying capital F primed of x equals little f of x. Then write down the answer, which is capital F of x plus c, where c is an arbitrary constant. And we talked about this back in section 4.9. right? Where I asked you for the most general antiderivative, you apply the appropriate kind of backwards differentiation rule to find your core antiderivative, or the thing that you know differentiates to little f. And then you slap on a plus c. And I just want to remind you that that plus c makes this not one function, but an infinite family of functions, right? It's all the functions that differentiate to little f, because this guy differentiates to little f, and no matter what c is, c will differentiate to 0. The indefinite integral of a function little f of x is the most general antiderivative of little f, and it's denoted integral f of x dx. And there's no numbers here, right? There's no a here, there's no b here. So this is just like the definite integral just without bounds. So if you see an integral symbol with no numbers, no a, no b, no like integral 1 to 5, just the integral of f of x, then that's a notation for the most general antiderivative. The important thing to remember here is that these are different animals. The definite integral, the integral from a to b of f of x dx, this is always just a number. It's, I mean, of course, it's the signed area bounded by f and the x-axis from x equals a to x equals b, but this is just a number. You know, the area is 1 or the area is 5. The type of object it is a number. If a and b are constants, actual numbers like 1 and 5 or 0 and 7 or pi and 2 pi, then this thing is a number. Whereas the indefinite integral, this is the most general antiderivative of little f of x, which is a totally different thing. This is an infinite family of functions. Okay. So they're very different objects. They look very similar, but they're totally different things. One of them is just a number. The other one is an infinite family of functions. Okay. So let's do a few examples, get a little bit of practice. I don't think you'll have a terribly hard time with this. The good news is that the indefinite integral obeys all the same rules as the definite integral. There's a reason we choose this notation. First, an example or two. I'm gonna switch. I have a blue pen here that I think writes a little better. So let's try the blue. If I want to calculate the indefinite integral of cos t.
Can you show the last page for a few minutes?
I'm sorry, what's that, Alejandro?
I'm not done with the last page.
Oh, okay. You can stay here for just a second longer.
Thank you.
Sure. Right. So if I want to do the indefinite integral of cos t dt, that means I need to find the most general antiderivative for cosine of t. Who differentiates to cosine? Well, sine. So sine of t is kind of your core antiderivative. And then you'd slap on this plus c. That's it. Easy as pie, right? If I wanted to find the indefinite integral of, x cubed dx, this is the most general antiderivative for x cubed when taken with respect to x. That's what the dx means. Just tells you what variable you would be anti-differentiating with respect to. So I would apply the power rule. This would be x to the 4 over 4. And then we slap on our plus c. Nothing mind-blowing here. This is stuff that you did back in 4.9. We're just using this new notation. Some properties of the indefinite integral include all the properties of the definite integral that don't have to do with the bounds. So if you have the indefinite integral of f of x plus g of x dx, and remember you should always write things like this with parentheses around the whole integrand. This dx should be multiplying both of these. That's the idea. And when we get to the section on substitution, that's going to be very important. So you need to get in the habit of putting your whole integrand in parentheses, even though some things you may see online don't do that, even though sometimes the textbook is bad about it. You need to do it. This, just like the definite integral, can be split up. It's the integral of f of x dx plus the integral of g of x dx. And if this plus were a minus, then this plus would also be a minus. The second really important property of this object, if k is a constant, then the integral of k times f of x dx is the same as k times the integral of f of x dx. So you can split up the integral over addition and subtraction, and constants pop out. These two features you may notice showing up a lot. The derivative had these two features. The definite integral had these two features. The capital sigma summation notation had these two features. These two features show up in a lot of places when you're dealing with operators, and they are called linearity conditions. These two things together say that the integral is a linear operator. Linearity of operators is a hugely important thing in higher mathematics, especially if you're going to study quantum physics or anything that has to do with functional analysis, operator theory, higher level calculus, essentially. So the other important properties that we have here, we can't have anything about like flipping a and b because there are no a and b, but if you integrate a constant dx, that will always just come out to that constant times x plus c. This is something that we've understand, right? That the most general antiderivative of 2 is 2x plus c, and there's nothing special about the number 2. Any other important properties here that I'm missing? I don't think so. I think that's the whole game. I'll just take a quick look. Yeah, you've got these things. We'll talk about those. But this is all that. Yeah, okay. So these are the properties of the indefinite integral that you need to know. And then you should look in the textbook. Look here on page 403. These things you guys need to know. These are all antiderivatives that we've learned in the past. The integral of a constant, or the antiderivative of a constant, is that constant times x. This is your power rule, right? If you want to integrate or find an antiderivative for a power, you add 1 to that power and then divide by that power. This works great for any power function, x raised to a constant, as long as that constant isn't -1, because the antiderivative for x to the -1 doesn't follow this rule. It follows this rule, right? X to the -1 is 1 over x. So who differentiates to 1 over x? Oh, that's natural log x. And we saw why we use the absolute values back in section 4.9. You guys are responsible for everything up to here. You need to know these. We talked about these in 4.9. These are all backwards versions of derivatives that I've told you need to know. Like the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Well, that means that the antiderivative for 1 over the square root of 1 minus x squared is the inverse sine function. All of these in the table, except for that bottom row, you guys need to know cold. Like you need to know them immediately. They should not be something you have to think about. So if in section 4.9 these didn't stick, make sure they stick now. And this notation of the integral instead of the capital F little f notation, is the more common notation that you'll see elsewhere in the world. Let's try a couple more examples. We can try something maybe a little bit harder where we have to use some of these properties. Example 1 looks good. 10x to the 4 minus 2 secant squared x. So we're going to evaluate the indefinite integral of 10x to the 4 minus 2 secant squared of x dx. How could I get started here? I want to use the information that we have from that table, right? The antiderivatives that we know, together with these properties. What would be a good first step? Yeah, I see something in the chat here. Yeah, we should separate them, right? We use this first property to say, okay, well, this integral is equal to the integral of 10x to the 4 dx minus the integral of 2 secant squared x dx. Now what? So here I used property 1. And in each of those integrals, I can use property 2 to pull out the constant multiples. This is 10 times the integral of x to the 4 dx minus 2 times the integral of secant squared x dx. And we had to split this up before I could bring out the constant. I can't bring out a 10 right away because 10 is not a factor of both of these pieces. The 10 only belongs to the x to the 4, so I had to split it up before I could bring out the 10. Similarly, this 2 only belongs to the secant squared, so I had to split it up before I can bring out the 2. And now we're golden, we're groovy. an antiderivative for x to the 4 can be calculated using the power rule. That's 10 times x to the 5 over 5. And I'm going to write plus C1 here because I've got two integrals. I'll have two constants. And then I've got minus 2 times an antiderivative for secant squared is tangent x. And I'll write plus C2 here. And then I can combine this into a single expression. 10 over 5, of course, that's 2. So this is 2x to the 5. And then I'll write minus 2 tan x. And then I'm going to put the C1 and C2 together into a single arbitrary constant, which I'll just call C. And remember that C stands for all the vertical translates of this function. So this is an infinite family of functions, all of which have derivative 10x to the 4 minus 2 secant squared x. Any questions on this example? Okay. So we can build a little from here. Let's try something like this. How would I go about doing this fellow? Somebody help me out. What's a good first step here? Split it all up, good. So if I split this up, I'm going to do kind of both steps at once. This is 3 times the integral of x squared dx minus the integral of 1 over x dx plus 7 times the integral of 1 over x squared plus 1 dx. Everybody on board with that? So you split it as the integral of this minus the integral of this plus the integral of this. And then the 7 can pop out of the last guy and the 3 can pop out of the first guy. Which means when I compute the integral here, I'll have 3, and then the integral of x squared is x cubed over 3. And I could write a little plus C1 here, but instead I'll just write it at the end. Minus the integral of 1 over x is the natural log of the absolute value of x, plus 7 times, somebody help me with this one. What is an antiderivative for 1 over x squared plus 1? Who has 1 over x squared plus 1 as his derivative? Feel free to open your book, look at that table. Good, the inverse tangent function. Yeah, Alejandra's got it. This is arctan, or tangent inverse of x. And though each one of these comes with their own little plus c, I can just write it at the end as a single plus c, right? So if you differentiate anything that looks like this, regardless of the value c, you will get exactly this. The only thing I would do before finishing up here is cancel these 3's. I would say, okay, so this is x cubed minus the natural log of the absolute value of x plus 7 times the inverse tangent of x plus a constant. Any questions on this one? Okay. So moving along then, how would I do this? I want to integrate quantity t plus 1 times quantity t minus 2. I'll tell you what I can't do. What I cannot do is integrate these two pieces on their own and then multiply them. That doesn't work. Just like derivatives don't play nice with multiplication, you need a product rule. Integrals don't play nice with multiplication. There is such a thing as a backwards product rule. It's called integration by parts, and you'll learn it in your first or second week of Calc 1. Or sorry, Calc 2. But here for us, there's a much easier way to do this. Does anybody spot anything I could do to write this in a way where I could figure out the antiderivative? Any algebra we could do? Yeah, go ahead and multiply them, right? They're being multiplied. Let's go ahead and FOIL that out. If I distribute this out, I'll get t squared plus t minus 2t, so that's minus t, and then minus 2. So while I don't know how to integrate this thing as it is, I don't know how to find an antiderivative for this thing as it is because they're being multiplied, and there's no nice rule for the antiderivative of f times g. If I FOIL it out, now it's all addition and subtraction that's separating the pieces. And now I can integrate each piece on its own. That's the integral of t squared dt minus the integral of t dt minus the integral of 2 dt, which is t cubed over 3 minus t squared over 2 minus 2t plus c, all coming from the power rule. Any questions on either of these examples? Okay, if not, then I'm going to continue on. Let's look at a few more. There's an important lesson to be learned from that last example, and we're going to apply it here as well. That last example involved some multiplication of functions. And I wasn't able to integrate until I kind of got rid of the multiplication, turned it all into just addition or subtraction. Here, my integral involves the division of some functions. And just like the integral doesn't play nice with multiplication, because the derivative doesn't play nice with multiplication, the integral doesn't play nice with division either. So does anybody see some algebra steps I could take here to rewrite this in a way that I can apply one of my rules? Yeah, we'll split it up. So the variable here is v, but what Josh said is correct modulo the choice of variable. This is v squared over v minus 2v over v plus the square root of v over v, all times dv. And again, notice the big parentheses. Now that the thing inside my integral is not a single chunk, now that I've split it into 3 separate chunks, I need these parens. This is just how addition and subtraction of fractions work, right? If you want to add 2 fractions or subtract 2 fractions, if they have the same denominator, then you just add or subtract the numerators. We're just doing this backwards. This is what you would get if you had a common denominator and put these together. So fractions can be split apart across their top. The general algebra rule here is one you all know, you're just not used to using in this direction. It's this. And now I can simplify each of those pieces. V squared over v is just v, minus 2v over v is just 2, plus the square root of v over v is v to the 1/2 over v to the 1. That's v to the negative 1/2. So this is v to the negative 1/2. And then I close my paren and I still have the dv outside. One of the mistakes I see people make is getting lazy and not writing the differential, the dv or the dx at the end. Don't be that guy. Don't be that girl. Always write your differentials. Always write the parentheses. Now I can apply my power rule. I can split this up, do each one of these on their own. The integral of v dv is v squared over 2 minus the integral of 2 is 2v plus the integral of v to the negative 1/2 is v to the negative 1/2 plus 1. That's positive 1/2. And then we also have to divide by that new power. And then finally, we slap on our plus c. This last term can be cleaned up a little bit. I would write this all as 1/2 v squared minus 2v plus dividing by 1/2 is the same as multiplying by 2. And then v to the 1/2, that's the square root of v. So I would say this is probably the nicest way to write that. Okay. So indefinite integrals aren't anything crazy. It's the same thing as saying find the most general antiderivative, just written in the integral notation. And remember how FTC2 works, right? FTC2 says if you're doing a definite integral, first you find an antiderivative, and then you plug in those numbers and subtract. So the antiderivative and this integral symbol are linked together. This integral symbol can really be thought of as the undo the differentiation symbol. It's the inverse operation to the derivative. I'm going to take a look here and see if there's anything we're missing. I don't think there is, though. No, we just did like this. We can play a little. Let's do a little more trig examples, and then we'll move on to the net change theorem. I like the one they had there, cos theta over sine squared theta. Let's take a look at that. This suffers from several problems. First, there's like some division of functions going on inside. That's a little scary. That doesn't look like any of my rules. Second, there's some trigonometry. Third, I don't know an antiderivative for sine squared, but maybe that doesn't matter. The only stuff that we know how to integrate in terms of trigonometry, we know the integral of sine, we know the integral of cosine, and we know their antiderivatives. I don't know the antiderivative for secant or tangent yet. Those will take a little bit of time. Is there any way I can rewrite cosine over sine squared in a way that makes it more friendly to deal with as an antiderivative? Well, how about I try writing it as cosine theta over sine theta times 1 over sine theta. Do we all agree that this is kosher algebra? If I multiply those two fractions together, I multiply the tops of the tops and the bottoms of the bottoms. So upstairs I would have cosine, and downstairs I would have sine squared. All right, this is the same. But cos theta over sine theta has another name. That's cotangent theta. And 1 over sine theta has another name. That's cosecant theta. And these fellows are being multiplied. And of course, you can multiply in whatever order you want. So this is the same as cosecant theta times cotangent theta d theta. Does anybody remember who has derivative looking like that? Looking like cosecant theta, cotangent theta? The derivative of secant, regular secant, is secant tangent Does anybody remember the derivative of cosecant? I'm going to pause on this for a minute. I want feedback from you guys. What is the derivative of cosecant theta? Cosecant, cotangent, almost. It's negative cosecant, cotangent. So there's this neat pattern with functions and their co-functions as far as derivatives are concerned. Okay, so what does that mean for my integral here? If the derivative of cosecant is negative cosecant cotangent, then what is the antiderivative for cosecant cotangent? Well, if I differentiate this, I get this. I want the positive version of this. So the thing I need to differentiate is negative cosecant theta in order to get cosecant cotangent. The derivative of regular cosecant is negative cosecant cotangent. So the derivative of negative cosecant is positive cosecant cotangent. And that's what I need. I understand that trigonometry here at Santa Fe is weak. I understand that. Trying to fix it. I don't know how it got this way, but trust me, there is no way to survive Calc 2 without remembering this shit right here. I presume you all want to survive Calc 2. Derivatives of trig functions and inverse trig functions will be huge in Calc 2, especially in the first few weeks. So you must get these things down. Any questions about what we did here? Okay. So then the next thing I want to talk to you guys about is actually a bit of a change of pace. It's called the net change theorem. And as a statement about mathematics, it's not anything surprising. It gets interesting when you start thinking about applications. I could say, you know, recall, well, I'll state the theorem first. So the theorem says that the net change in f primed of x, no, I should say it like this. The net change in f of x, no prime here, is equal to the integral, and this is a definite integral, the net change in f of x, from x equals a to x equals b is equal to the integral of f primed from a to b. This is how your book says it. And this shouldn't be anything surprising. The proof is immediate. Recall that the net change for a function f of x from x equals a to x equals b is defined to be f of b minus f of a, right? It's the average rate of change just without the denominator. Net change is as you went from input A to input B, how much did your outputs change overall? What's the vertical distance between the starting point and the ending point? So by FTC2, the integral from a to b of f primed of x dx, an antiderivative for f primed is just regular old f. And we need to evaluate that from a to b. And that is f of b minus f of a, which is the net change. In f of x from x equals a to x equals b. Nothing fancy, right? It's just real straightforward. The neat thing happens here, when you start thinking about applications, there are some specific functions whose derivatives are related in interesting ways that have meaningful applications in physics. Like the derivative of your position, if this is your position, its derivative is your velocity. So if you know the velocity at every moment in time, you can figure out the net change in position, which is called displacement. There's a lot of other applications here too. Your textbook outlines a handful of famous ones. I'll show you. Switching to the textbook now. All right, so this is what you think it is. The net change in a function f is the integral of f primed from a to b. The first example here, if v is the volume of water in a tank or reservoir at time t, then its derivative is the rate of change of the water coming into the tank. So imagine you're filling a bathtub and you know that 1 gallon of water comes in every 10 seconds. That means you know v prime. You want to know how long will it take to fill the bathtub? Well, integrate v prime, and that will tell you how much water is in there. The change in the water from time t equals 1 to t equals 2. If you take some vinegar and some baking soda, you know those two things react together. Well, suppose you know that during that reaction, the amount of baking soda that's left in your solution is decreasing at 1 gram per second. Then you know the derivative of the concentration is 1 gram per second, or -1. If you integrate that function, you can figure out how much baking soda is left in your solution t seconds later. There's a few other examples here, the most famous of which is at the bottom. If you have an object in motion, then its velocity is the derivative of its position. So if you integrate the velocity, you can find how far the object ended up from where it started, which is called the displacement. Displacement is not the same thing as total distance traveled, but there's also a nice relationship there. So I'm going to switch back to the dot cam. If an object is moving along a straight path, and has velocity function v of t, which remember is s primed of t, then the total displacement and remember, displacement is a word that just means how far did you end up compared to where you started, is total displacement from time t equals a to t equals b is going to be the integral from a to b of v of t dt, which is going to be s of b minus s of a, your ending position minus your starting position. All right, this can be positive, this can be negative, this can be 0. If you end up where you started, if you go forwards 10 feet and then backwards 10 feet, then your displacement is 0. And no matter what that velocity function looks like, that integral will come out to 0. On the other hand, if you know your velocity at every moment, have you guys heard of the app, my phone on me, the phone app Strava? Anybody like to ride bikes? Gainesville's a big bike town. Strava is a very popular app for tracking your bicycle rides. It tells you, you know, how far you went, and it tells you what your path was. It tells you all this good stuff. This is how Strava works. Strava takes a sample every second or so of your velocity, and then it integrates that function numerically to find how far you went. A note, displacement is not the same as distance traveled. Right? Like the example I gave you. If you go in a loop, then you finish where you start. Your displacement is 0. But you definitely didn't travel 0 feet, right? If I go on a 1 mile jog around my neighborhood, then my displacement is 0, but I traveled a mile. The distance traveled is the integral from A to B of the absolute value of V. In other words, if you're moving forwards and backwards some of the time, then your displacement is not going to be the same as your total distance traveled, right? If I run back and forth, you know, on a 10-foot straight path, just back and forth like 5 times, then I've traveled 50 feet, but my displacement is 0. The reason the integral would come out to 0, the reason this integral would come out to 0, this displacement integral, is because sometimes this velocity function is positive when I'm moving in the positive direction. And if I'm moving in the negative direction, that velocity function is negative. In other words, some of the area being measured here, if you think about the graph, could be above the x-axis, could be below the x-axis, or I guess in this case, t-axis. So if your velocity function is always positive, then this integral, the displacement integral, will give you your distance traveled. But if your velocity function is sometimes positive and sometimes negative, then to get the total distance, you need to integrate the absolute value of your velocity function. So the textbook has an example of this that is acceptable. We can take a look at that. Right, so here they have a little discussion on exactly what I just said. If your velocity is sometimes positive, sometimes negative, then this area, remember, is going to be measured negatively by the integral. So the displacement is just the straight up integral, but the distance is the integral of the absolute value, which is going to make all these areas positive. So let's do example 6 here. T squared minus t plus 6. The particle is moving along a straight track and has velocity function v of t equals t squared minus t minus 6. Find the displacement from t equals 1 to t equals 4, and part B, find the distance traveled I think, from t equals 1 to t equals 4. So the displacement is just the integral. The integral from 1 to 4 of v of t, which is the integral from 1 to 4 of parentheses t squared minus t minus 6 dt. We can find an antiderivative for this function. We're using FTC2 to evaluate this integral, so we find an antiderivative. and then we plug in the endpoints. So an antiderivative for this fellow would be t cubed over 3 minus t squared over 2 minus 6t. And I'm going to evaluate this from t equals 1 up to t equals 4. We always do the upper bound minus the lower bound, so I'll plug in my upper bound. When I do that, I get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. And when I plug in my lower bound, I get 1/3 minus 1/2 minus 6. And this number, we could crunch it out. This is 64/3 minus 16/2 minus 24. 16/2 is 8 minus 24. And then minus 1/3 plus 1/2, distributing this negative plus 6. I am going to cheat a little bit here and use Desmos to do the calculation because I don't want to burn time. Click home. Scientific calculator. There, 64/3 minus 8 minus 24 minus 1/3 plus 1/2 plus 6 and negative 4.5 or negative 9/2. Or negative 4.5. Right? So if this velocity is like feet per second, then after we finish this, we go from t equals 1 to t equals 4. We finished 4.5 feet behind where we started. That's what this means. Right, that's how we would interpret this, or 4.5, sorry. That's what displacement is. So at time t equals 1, we start, we move around a little bit, we finish with displacement negative 4.5, meaning we finish 4.5 feet behind where we started. Questions on part A? Okay, part B is a little trickier. Now, if my particle was only ever moving backwards, then that negative 4.5 would tell me how far I went. It means I just started somewhere and moved 4.5 feet back. But this velocity function is not like that. This velocity function is not always negative or always positive. T squared minus t minus 6 factors as, what is that? 2 and 3, right? That's t plus 2 times t minus 3. So what's the graph of this look like? have x-intercepts here at -2 and +3. My vertex is probably somewhere down here. So the graph of this function is this parabola. And we're looking from t equals 1 to t equals 4. That's the piece we're interested in. So sometimes he's negative, and sometimes he's positive. And the total distance is the total area here. And I need to make sure that I'm not counting this area down here as negative, which the regular integral would. So our total distance is the integral from 1 to 4 of the absolute value of v of t. Now, how the hell do I make this work out so that I count this piece as positive rather than negative? Well, the trick is to use some properties of the definite integral that we discussed last time. Remember, the definite integral can be split up. This is the same as the integral from 1 to 3, absolute value v of t dt, plus the integral from 3 to 4 of the absolute value v of t dt. From 1 to 3, my function is negative. From 3 to 4, my function is positive. So from 3 to 4, I don't need to do anything. But from 1 to 3, I need to negate this to make it positive. So this is going to be integral 1 to 3 of negative v of t dt, because v of t is itself negative from 1 to 3. So to make it positive, to do what the absolute value function says to do, I need to negate v from 1 to 3 to make that part positive. And then this other part I leave alone, integral 3 to 4, regular v of t dt, because this piece was always positive. What I'm using here is the definition of absolute value that maybe you recall, maybe you don't. Absolute value of some shit is that shit if that shit happens to be greater than or equal to 0. But it's the negative of that shit if that shit is less than 0. So here, my shit is less than 0. So the absolute value of my shit is the negative of that shit to make that shit positive. Making sense? Now from here, I just have to compute these two integrals, neither of which are hard, but it is a bit of arithmetic to do. So I'll continue it over here, try and give myself as much space as I can. This is the integral from 1 to 3 of negative v of t, which is negative t squared minus t minus 6, plus the integral from 3 to 4 of regular v of t, which is t squared minus t minus 6. This negative can come outside the integral. And this guy just chilling. My next step is to find an antiderivative, and the antiderivative for each of these pieces look very, very similar because, of course, the thing inside here is the same. So this first guy is going to be negative t cubed over 3 minus t squared over 2 minus 6t. Same antiderivative we found before. And he's going to be evaluated from 1 to 3. This plus is this plus. This guy has the same antiderivative, t cubed over 3 minus t squared over 2 minus 6t. And he's going to be evaluated from 3 to 4. So we can go plugging things in. This first guy, I have negative 3 squared over 3 minus 3 squared over 2 minus 6 times 3. That's the upper bound for the first guy. And then I need to subtract the lower bound for the first guy, which is 1. That's 1 cubed over 3 minus 1 squared over 2 minus 6 times 1 is just 1. And then we're going to add this to what we get when we evaluate this piece. At 4, this is 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. And at the lower bound here, we have 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. And you may notice two pieces showing up, or one piece showing up in both of these. This piece and this piece are the same. So I'm going to distribute this negative to these two big chunks here. I'm just going to write this as negative 3 cubed, that's a cube, over 3 minus 3 squared over 2 minus 6 times 3. That's this negative hitting this piece. Now this negative hits this piece, so that'll be plus 1 cubed over 3 minus 1 squared over 2 minus 6. And then these guys were already positive. I don't need to distribute anything here, so I've got 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 and minus 3 cubed over 3 minus 3 squared over 2 minus 6 times 3. Negative. Let's see. So if we want to simplify all of this, you can observe that these two things are identical. You could combine them, and the rest of it you just have to crunch out. So we'll have negative 2 copies of 27 divided by 3 is 9. 3 squared is 9 divided by 2. Minus 6 times 3 is 18. Then you have plus 1/3 minus 1/2 minus 6 plus 4 cubed is 64. So 64 thirds minus 4 squared is 16. 16 divided by 2 is 8. Minus 24. And again, depending on how lazy you're feeling, you can use a calculator to do the arithmetic here for you. I will go ahead and do that, so we're not wasting your time. So we have negative 2 times 9 minus 9/2 minus 18, close parentheses, plus parentheses 1/3 minus 1/2 minus 6 plus 64 thirds minus 8 minus 24. So we get 61/6 or as a decimal. What was that? 10.16 repeating. So this is my total distance. And of course, the total distance is larger than the total displacement, because part of the time I was moving forwards, part of the time I was moving backwards. Right? From time t equals 1 to t equals 3, my particle was moving backwards. And then from t equals 3 to t equals 4, it was moving forwards. I know it spent more time moving backwards than it did forwards, because the total displacement, the displacement was negative. I ended up 4.5 feet behind where I started. But I did that by moving back for a long time and then moving forwards a little bit less. So my total displacement came out negative 4.5 because I spent more time moving back than forwards, or I was going faster backwards than I was going forwards, or both. But my total distance is a positive 10.16. Questions on these calculations? Or the setup? The setup is the most crucial part to understand here. You've seen this before, back in the Riemann sum homeworks, where the area under the curve was your distance, right? The area under velocity is distance traveled. That's true as long as the velocity function is positive. But if the velocity function is sometimes positive and sometimes negative, then the total area bounded by the curve is your distance. And the regular integral will measure some of that area as negative unless you take absolute values. Alrighty. Well, gang, that is all I have for you this week. Yeah, they get 10.17. Oh, and we're right on time. Okay, so please work hard on your homework. There's plenty of things like these, right? Just calculate the antiderivative, but you're using the integral notation now. Try to get comfortable with the notation. And then challenge yourself on the application problems. If that last problem felt a little bit weird or a little bit scary, where we involved an absolute value, I can strongly recommend that you try a few of these later problems that have absolute values in them. Especially if you're having a hard time with the difference between distance and displacement integrals, you will find these very helpful. Next week, we're going to talk about a few things. Because next week is the holiday week, I don't want to dump 5.5 on you all the way yet, but I would like to introduce 5.5. This is a challenging section. This is the section that I've kind of been warning you about. Please read this section, it will help you a lot. The other thing that we're going to be talking about are some neat theorems. There's a mean value theorem for integrals here. And so I'll talk about the two mean value theorems. There's a mean value theorem in terms of derivatives also. The one for integrals is nicer. The other thing we need to talk about is differentials, which are similar to kind of something we did in the past, but it's necessary in order to prepare you for the notation of 5.5. So I want to encourage you to read carefully the sections that we covered this week. 5.3 and 5.4 are both hugely important. You can smell that because they're called fundamental theorem of calculus, and this one defines a whole object, the indefinite integral. And then come ready on Monday for us to work hard. All right, these last few sections, especially 5.5, which is the next one in order, is a hard section. Students tend to have a difficult time with this. The syllabus, if you look, says we're going to talk about a few other things like differentials, applications. The application stuff we did just now. Differentials are really just like a little tiny thing I need in order to teach you 5.5. So next Monday, I'm going to start off talking about differentials, and then we're going to jump into 5.5. 5.5 again is challenging, so you will need to prepare yourself for this by reading the section. Please read that section. That is all I have for you today, ladies and gentlemen. Are there any questions you would like to ask me before we depart for the afternoon? Alrighty then, I will see you guys either in office hours or on Monday. Take care.